Today's step question is from 2019. It is question 2, and it's a question on parametric curves. These questions are nice because they bring together algebraic understanding and techniques with visualization and geometry. So we're told the curve C is given parametrically by the equations x equals 3t squared and y equals 2t cubed, and we're being asked to show the tangent to the curve at a point with parameter p is y equals px take p cubed. This is essentially an A-level question on finding tangents to curves. The difference being that you're probably not familiar with this particular curve, which is called a semi-cubical parabola. I do recommend trying to sketch the curve first of all, and the key features of this are it is symmetric in the x-axis, which is shown by the equations there. It has a cusp at 0, 0, that is, it comes into gradient 0 both above and below the axis. It's called a semi-cubical parabola because if you were to eliminate t, you would get a multiple of y equals x to the 3 over 2. So I've drawn a tangent at p, and we're trying to find its equation. So for the gradient, dy dx working parametrically equals t. So the tangent at point P is y minus 2p cubed equals p times x minus 3p squared, which simplifies into y equals px take p cubed. Now be careful here to distinguish between t, which is a variable, it is the parameter in general, and p, which is a fixed point of the parameter. So we don't want to see anything like dy dp or dx dp, and we don't want to see the final equation having t in it. Step examiners can get fussy about things like that. Next part, we're having another tangent at a point with parameter q, and we want to find its point of intersection. So I've drawn two tangents there, and we're trying to find where they meet. So, and we're also told that as well, we're going to have the parameters, the two lines, to be perpendicular. So after we've found where they intersect, we're going to use the fact that PQ equals minus 1 to simplify. So the tangents will intersect when px take p cubed equals qx take q cubed. Taking x to one side and the other variables to the other side, I get p take qx equals p cubed minus q cubed. And this is what I mean by using nice algebra. That is a difference of two cubes, and really you need to know for step the factorization of p cubed take q cubed is p take q times p squared add pq add q squared. P is not equal to q, so p take q cancels, giving us the general result that x equals p squared add pq add q squared. We are then told in the question that pq is minus 1, the two tangents are perpendicular, and we want to rearrange that into the form of u squared plus 1, where u is p plus q. So p squared add pq add q squared is p plus q squared minus pq. Once again, using some standard algebra, the expansion of p plus q squared, which is u squared plus 1. In this question, they both want the general form, and then they want us to use p cubed equals minus 1. We have to do both to satisfy the question. We now need the y value. Y is px take p cubed, so putting the x value in that we've just found, that simplifies in general to pq times p plus q, and then using u equals p plus q and pq is minus 1, we get y is minus u. So if the 2 points are perpendicular, the two tangents to the points are perpendicular, we get the point of intersection u squared plus 1 minus u. Now, it now says in the question, we've got two curves. The original one is C, and C tilde, that is with the wiggle over it, is x equals u squared plus 1, y equals minus u. You will recognise that, I hope, as a parabola on its side. And we want to find where these two curves meet. So we're going to solve simultaneously the parametric forms. U squared plus 1 equals 3t squared, and minus u equals 2t cubed. So various ways of doing this. I've eliminated u to give 2t cubed squared plus 1 equals 3t squared, which simplifies into the equation of order 6, 4t to the 6 minus 3t squared plus 1 equals 0. That is, of course, a disguised cubic using t squared as our unknown. And with a little bit of work, that factorizes into t squared take 1, t squared take 1, t squared plus 1. Factorizing cubics is something to work on. Here it might take you a little bit of work to do it. So the curves intersect in three places when t squared equals a half, and that is repeated, or t squared equals minus 1. In this question, we can discard t squared equals minus 1. T is a real number, it can't be. And since t squared is a half, is repeated, we are having the curves meeting, in fact, at points where they are tangential. So working out what those points are, using t squared as a half, we get x equals 3t squared, which is 1.5, and y equals 2 times t cubed, so plus or minus a half times 1 over root 2, which is plus or minus 1 over root 2. And I give the coordinates there as asked. We're now asked to draw the two curves on the same axes. We need to make sure we do show that the curves are tangential to each other at the points of intersection. So here we have it. So the green curve, which I've marked as C, is our original semi-cubical parabola. The red curve, C tilde, is our parabola, which cuts the x-axis at 1, and the curves meet when x is 1.5 and y is 1 over root 2 or minus 1 over root 2, and you can see there what's going on. The two curves are touching one another at those points. Make sure it's clear which curve is which, so make sure that you do mark them. I think that's a nice question. I think that's nice geometry, and I've actually drawn the curves again using an online package, which you won't have in the exam, but I think it illustrates quite clearly what's going on. So we have the original semi-cubical parabola, which I've indicated in its two branches by these red and blue curves. We have 2 points on the parabola with tangents at right angles. So the black straight line and the red straight line are tangents, and they are at right angles to one another. And you can see that they are meeting at this point here, which is indeed on the parabola that we have found. I've drawn the parabola, and you can see it touching the original curve when x is 1.5 and y equals 1 over root 2, which is roughly 0.7, both above and below. If you were to take a set square with a right angle, you could construct that parabola by putting the set square inside the semi-cubical parabola and moving it around, and the apex of the set square would move round. The locus would be the parabola. I think that's a nice question. You might like to think what would happen with other curves if we did something similar. So, for example, if we started with a parabola and took two tangents at right angles, what would the locus of their intersection be? What about for an ellipse? In general, these are going to get quite complicated curves, not necessarily as interesting as the one we've started with, but it's certainly worth trying it with the conic sections, with the ellipse and the parabola, to see what you get. So, a nice question, well worth being able to do these. They are standard techniques, some standard algebra as well, the difference of two cubes, difference of two squares, factorizing cubics, all standard things that you really want to be fluent in before you attempt a step question. So, that's this week's stepped question. I'm David Forster. This is Gold Standard Math.